Thanks for offering me this possibility. Those of you who know me, I work a lot on the Galactic Centre, usually in the near infrared. So this talk has cost me a bit of work. I hope it will satisfy you. So first of all, a small word, the Galactic Centre. So I come from the black hole, but I have moved out over in the last decade. So for me, the Galactic Centre is basically a nuclear bulge. I hope that is adequate for everyone, so we can put in a lot more things, and there's star formation going on there. So, right, now here we go. Let's first start out with some more general remarks in addition to what I've just said. So the Galactic Centre is, of course, a fantastic target because it's the nearest galaxy nucleus. It's just at 8 kiloparsecs. This is much better. It's if you want to go to Andromeda, you're 100 times away, and if you want to go to AGN, you're already 1,000 times further away. Nevertheless, it also has some extreme problems, which is above all extinction. So in the visual, we get above 30 magnitudes, which is a good reason to go to the infrared, particularly to the thermal infrared. It is, to a certain measure, particularly when you average it by volume, when you normalize by volume, it's definitely the most active massive star forming region in the Milky Way. So maybe 10% of all the Milky Way's Lyman alpha photons come out of the central 100 parsecs or so. It has some pretty unique properties of the interstellar medium. So we have very high magnetic fields there. So it's 10 to 100 times higher than in the spiral arms of the galaxy. We have relatively high temperatures of the interstellar medium. It's much more turbulent. There's lots of cosmic rays around. So one may expect that this can have influence on things such as star formation. And now our thermal infrared observations. So I will go thermal. For me, it's roughly around 5 to a bit beyond 30 microns. I will talk about 3 microns as well. So mostly it's find, count, and characterize the potential young stellar objects in there in the Galactic Centre. Of course, we can study magnetic fields nicely and also the interstellar medium with spectroscopy, fine structure lines, etc. Then something that is a promise for me for the future for James Webb is study the stellar populations and stellar structures. We've used Spitzer there a bit, but it's low angular resolution yet. Then of course study what goes on in and around the Sagittarius A star source, so our massive central black hole. How do accretion emission processes operate there? And then we see also some dusty stuff that is floating around and may actually feed the galactic black hole. And of course, we always have an enormous discovery potential. So here is a nice overview. I found this beautiful image in a publication from Farhad Youssef Zadeh, 2009. So this is Spitzer 3.6, 8.0 and 24 microns across 2 degrees. So that's 290 parsecs across. That's basically the entire Galactic Centre. It's the entire inner nuclear stellar disk. And if you can, I hope you can see my mouse here. So here in the very center, so the dashed line here is the galactic plane. We have then the nuclear star cluster and SAGA star right in the center, almost point-like on these scales. You can see there's lots of the greenish stuff is mostly PAH emission. And surprisingly, we also have lots of infrared dark clouds. So there's lots of dense material floating around, for example, in the SGB2 region that is currently maybe the most active massive star forming region in the Milky Way, still entirely obscured. Even at the thermal infrared, there's not much visible here. SGB1, which is a more recent star, which is a bit older star formation, star forming region, you see a lot. Then there's also completely inert molecular clouds, although massive and dense, like the brick and SAGA C, for example. So you see there's a whole richness of things to be explored, also the arches and quintuplet clusters, which are 2 of the most massive young star clusters in the entire Milky Way. As concerns extinction, here you see from this work from Tobias Fritz from 2011, they basically used lines. They show a nice extinction law here from the visual to the thermal infrared to 30 microns. And you see that extinction is a really steep function of wavelength in the visual to the near infrared. And then it flattens out at around 5 microns where it has a minimum. So this is very interesting. We just have a magnitude of extinction here. We are already at 2 to 3 magnitudes at 2 microns. So this is highly interesting. And then if you go to longer wavelengths again, silicates become a problem and also absorb lots of lights again. Well, not as extreme as in the near infrared. So here you have your minimum. Now let's start with two surveys, thermal infrared surveys of the galactic center. That means we basically have to go to space, because from the ground we only observe at high angular resolution very small fields, because if not, the photon noise kills us immediately, the background. So the standard currently is, I would say, the Spitzer Galactic Centre survey that was led by Susan Stolovy. It's published in 2006. It is so far still the most sensitive, highest angular resolution thermal galactic center survey to date. It has, although only 2 arcsecond angular resolution, because it was just a 60 centimeter telescope. So this is a big problem with confusion in the galactic center. Because in 2 arcseconds, Gaussian, you can fit dozens of stars in there, or even 100 stars easily. It has a large field of view, so 265 by 200 parsecs, all IRAC channels. And well, then you see lots of infrared dark clouds there, of course. You can study the interstellar medium filaments, Paschen PAH alpha emission, not Paschen, polyaromatic hydrocarbons. You find lots of H2 regions, and then up to 1 million point sources, which are published in Ramirez et al. 2008. It looks like this. So this is one of the most publicized images I've seen so far, and I think not only for people who actually work in the Galactic Center. So this is NASA Caltech, Susan Stolovy. You have this beautiful multi-wavelength region of the Galactic Center. So you see all the PAH emission in red. You see the molecular clouds dark. You see the star-forming regions, SGC. The arches and quintuplet clusters, although they each contain more than 100 O and B stars, they are just a few pixels on this thing. It's quite impressive. That's what you see, how this stuff is reduced. These are immense clusters. And then you see very clearly the nuclear star cluster of the Milky Way. SGA star itself is invisible. If you go to long wavelength in the same survey, so the same field of view at 8 microns now is really dominated by PAH emission, but there's some interesting objects. So for example, if you go here, you have this nice, beautiful H2 region close to a molecular cloud. Then if you go towards the quintuplet massive cluster, this is a zoom here. Can you see my mouse? Yeah, okay. So this is the famous quintuplet sources. The rest of the cluster is almost not visible at 8 microns. And then you see here this wind-blown bubble and the so-called pillars of creation here also. So you have induced star formation at the edge. And for example, if you look here, that is the so-called mini spiral round. This is this super exposed part here, it's different scale. So this is some ionized gas right around in the core of the nuclear star cluster and around the massive black hole. Now another survey that is just, well, going on or just terminated maybe is a SOFIA FORCAST Galactic Center Legacy Survey at far longer wavelengths. So that's 25 and 37 micrometers. So we're already edging out of the thermal infrared here. And to save time, they do not observe the entire field, but just what you see framed in white here. It's also 403 square arc minutes, and they basically focus on the central regions and all the H2 and star forming regions. To show some details, you've seen before the quintuplet cluster. So here quintuplet sources, and very spectacular here, this bubble around the pistol star. The pistol star is one of these sources that is thought to be the most massive star in the galaxy that we know of. Of course, then it's really unstable and throws out lots of material. Then you have here these pillars again that point towards the cluster and that are wind blown here. You have this nice bubble here. And this is the environment of Sagittarius A star. Again, the central few parsecs are extremely strongly exposed, but what you see also is these filaments going off here. So maybe you see some signs of outflows that we will also talk about later at smaller scales. And then of course you see H2 regions that I will mention later. So apparently we have some ongoing star formation around 10 or 15 parsecs from the black hole. So let's focus on star formation now in the galactic center. Of course, we have a nice traceable star formation with thermal infrared in particular, because now we don't have these problems with the extreme extinction. And there's a big interest now. There's lots of dense molecular gas in the galactic center. But one of the big discussions or the big problems is if you apply extragalactic scaling laws, for example, the amount of dense molecular gas that is available predicts you a much higher current star formation rate than what you actually observe. So the big question is that a problem of specific to the galactic center, because maybe you have higher magnetic pressure, which is also one of the discussions whether you favor massive star formation at the galactic center. And of course, now very important to really know what the current star formation rate is counting YSOs. There have been claims that a starburst happened about 10 to the 5 years ago, and a big discussion going on. It's not at all clear here. So there's really big discussions. I will mention now one of the last papers here, this Nanda Kumar et al. 2018. They actually take photometric identifications of YSOs by other people that have been identified mostly in the mid-infrared, maybe adding a bit of near-infrared to there. And they have spectroscopic information on a few dozens of stars. And it's quite interesting that they find that the photometric identification criteria that have been used are very ambiguous. On the left-hand side here, you see this plot, and they use what has been used before by other authors, 8 minus 24 microns versus 24 microns color magnitude diagram. And what they find is that everything is all over the place. So late type stars, in particular HEB stars, can also be relatively bright in the near infrared, and they can really contaminate you. Here's some YSOs, there's a non-YSO interloper. So it's not clear at all how you would select here. Then they take the spectroscopically classified samples. So they have looked at putative YSOs and found many of them are late type stars, HEB stars, for example, but some of them are YSOs. And then they use H minus KS versus H minus 8. And here they say, oh, we can separate the brightest of these sources relatively well. Not perfectly, but this is a nice new criterion they suggest. They say it still needs to be investigated. SOFIA FORCAST, there's also studies going on of star formation. It's quite interesting now. They find this is some H2 regions that for some reason are designated with the letter H. So it's the H2 regions, and there's an H2 region, so far from confusing numerology. But they also find a lot of very faint apparent H2, ultra compact H2 regions, which is very interesting. They find that some of these H2 regions, like this H1 source here, they really can only be explained with a massive ionizing source in place, having formed in place, while other of these H2 regions may actually be interlopers. So that could be massive stars that were ejected dynamically from the arches or quintuplet cluster. Nevertheless, it's quite interesting that they find these smaller sources too. So that again suggests a big discussion that has been going on for a decade in the galactic center. Do you just form massive clusters there? Do massive stars only form a cluster, or is the galactic center perhaps an exception where massive or relatively massive stars may also form in relative isolation? Now, one of the major, if not the major result of thermal infrared in the galactic center is also SOFIA, and that is from Ryan Lau. It's a Nature paper in 2015. And that's discovery of dust inside the supernova remnant Sagittarius A East. You see it here. So this is an outline. I think the red is, no, blue is X-ray and red is 31 micrometers also. And you see here, no, the contours is 6 centimeters is the red one. So this is the supernova remnant. You see this shell here. And then you see the outlines at 31 micrometers. And this is really dust. You see it in a nice color image here. That is clearly associated with the supernova, and it has formed and survived the supernova and even survived the reverse shock. Now, that is, it's not much. I think it's like 2% of the solar mass, but it's vastly important because it says that dust can survive supernova, and therefore supernovae can be actually dominating in the dust production in the very early universe, because we need to produce dust in order to efficiently cool the ISM and then form the next generation of stars. So now let's go towards the central parsec. Haven't been paying attention to time. No, we're doing well. So some of the earliest spectroscopic observations and really pathfinder was ISO, that's Infrared Space Observatory So this is SWS spectroscopy of the Galactic Centre for the first time by Dieter Lutz et al. From MPE. And they find that the fine structure lines indicate an aging starburst population, which was already roughly known there and has been spectacularly confirmed also by integral field spectroscopy in near infrared. So we know that a few million years ago there has been a starburst happening close to Sagittarius star. They find lots of PAH in the molecular ring around Sagittarius star. And also quite interesting that the mid-infrared extinction is significantly higher than what had been theoretically predicted by the Drain extinction law, for example. Now, if you want to go to early 10 micron imaging, we go to Eric Becklin and Jerry Neugebauer, who are actually, for me, heroes because they discovered the Galactic Centre in the near infrared or observed it first. They used these single pixel detectors, here in the case in the Hale 200-inch reflector. And not only did they the first near infrared observations, but also the first 10 micrometer imaging. Well, Ricci and Lowe also have to be mentioned here. So it's the beginning to middle of the 70s. We have 2.5 arc-second resolution. And they find this so-called mini spiral here. They find it's heated dust that is probably optically thin, so like in a typical H2 region. And they also designate at least 5 or more compact discrete sources. And we still are not stuck with the numbers they gave to these sources in the 70s. This is now a complete change. This is now almost this is 50 years later. This is now a VISIR on the VLT with the newest, after the upgrade with the Aquarius detector. It is one of these data sets that have been taken as spectacular and not published. So shame on me. And if you are in the proposal committee on ESO, please don't hold this against us. I know there's other people among you guilty of that. So these are spectacular images of the mini spiral now. They have been treated a bit more. I've treated them with my speckle holography algorithm. So we have now really fully diffraction limited images here. It's a program from Daniel Asmus, Konrad Tristram, and myself. The idea was trying to discover Sagittarius star. And you see really, this is the same image, just at different scaling so that you can appreciate the filigrane structure, the extremely complicated filaments that you see here. At further out from Sagittarius star, but also close to it, you see there's this, it looks like a wind is blowing out stuff here. You see this tail of the supergiant IRS-7, which can also be seen in radio. You see this bow shock source from IRS-3. You see these things here. This is called the mini cavity that has been known for a long time. Other cavities, you have these filaments, you have kind of corkscrew effects here. So you see, you can already have an idea that the magnetic fields play a role here. So it's incredibly rich, and to my great delight also we see several dozen stellar sources here on the left-hand side also. So it's really sensitive. This is at 8.6 microns, by the way. So spectacular stuff that can be done by now. Now the surrounding, so what we've seen now is this part here. And now we go back to SOFIA again. There's a circumnuclear ring or disk, it's called, of molecular material around Sagittarius star that has the rotation of this gas has even been used for early estimates of the mass of the black hole. And now what you see in the thermal infrared and then also in the near infrared and the Paschen alpha is the ionized inner edge of this molecular ring, which you see here nice in the model, as from Lau et al. Also from Ryan Lau. So, and they've really find a classic H2 region describes this very nicely. We know we have like 10, 15,000 solar masses and mostly massive, we have more than 200 massive stars in the central 0.5 parsec. So there's lots of radiation that can heat this to temperatures up to 65, 85 Kelvin. And they find a surprisingly small mass, of course, not for the entire ring, but just the stuff that is illuminated is just 600 solar masses, which is an order or 2 orders of magnitude smaller than what was found by other people. Here's another cartoon image of this from Patrick Roche. You have kind of this ring, and then you have the infalling ionized arms. This is the northern arm, and then you have this east-west bar in the Galactic Centre. Now, quite spectacular. It becomes spectacular now if you see what Pat Roche et al. Have been doing with CanariCam. CanariCam is a cool instrument. It's unfortunately not very suited for the Galactic Centre because it's very far in the north, but it's the only mid-infrared polarimeter. And so this is what it sees in the Galactic Centre. So on the left-hand side is this artistic view, this has been done for this field lines also in, I think, the boomerang experiment and this. So we have the magnetic field lines here really that are indicated, and the polarization degrees are high here. It's more than 12 degrees. We see the filamentary structure. We see the field lines really follow the filaments out here and here. They are compressed by the flow around SgrA star. Even here you see them nicely following SgrA star down to SgrA star. You have some compact sources that disturb the flow. They actually wrap around there and they change the polarization degree. And this is 1 arcsecond resolution at 12.5 microns. I wish we could do this at 8.6 microns with VISIR, but unfortunately we don't have polarimeter there. So this is really tells you something about the importance of magnetic fields in this environment. And of course there's all these publications that have preceded this work. Now let's go to the very central few arcseconds. Of course, we have to talk about SgrA star. How am I doing with time? I think I need to. Well, okay, yeah, I'm still okay. So SgrA star was discovered as a highly variable source in the near infrared to the short thermal infrared. It's clearly from the minute variability that we see emission from near the event horizon. It's polarized emission, so this is a near infrared result, not thermal, but it's polarized, so it's clearly non-thermal. It has a variable spectral index. And quite successfully, it seems that sometimes there seem to be hotspots circling around the black hole, as has been also observed by the gravity collaboration. If you go to longer wavelengths, around 8 to 10 microns, there have been numerous attempts to detect SgrA star at these wavelengths. I've myself been involved in 2 of them, and we've never been successful. The big problem is that noise picks up a lot and the angular resolution goes down while we have lots of junk floating around in the galactic center. So this is just a like 5 by 5 arcsecond image. Here you see SgrA star, an error cross, and we have this thing, which I term the SgrA star ridge. This is dust that is unrelated and it almost sits on top of SgrA star, so we can just infer upper limits and we cannot detect any flares. So not published, but so far nobody has ever found anything there. It's really confusion with dust mainly. As I've mentioned already, quite interesting in thermal infrared where we can see the interstellar medium. We see these cometary features. I've mentioned it around this star, and you see here this IRS3 star, but you see that the filaments are aligned in these ways. You have these X3, X7 filaments that have been pointed out by earlier work by Kora-Music. Kora-Music also found that these filaments here, they do not really seem to move in Keplerian way. So we have some wind pressure here that can be outflows from the stars or also from the black hole. We know there must be outflows from the black hole. We also see, as pointed out by Farhad Youssefzadeh, cometary features closer to SgrA star. So there's clearly lots of evidence that the center point, few 0.1 arcsecond drives strong outflows. And we also find very compact objects, partially resolved, partially unresolved, at a few tenths of a parsec, or even a few below 0.10, I mean, extremely close to the black hole. If this is the black hole, this is, I mean, at a few tens of milliparsecs, we find, or milliparsec distance, these dusty sources. We don't really know what they are. They're highly discussed, but at least this co-moving source, and there are some co-moving sources that can be very possibly young stellar objects, actually, very close. So actually ongoing star formation close to SgrA star. So one of these dusty objects really made furore, was really very famous. It's a so-called G2 object, as published by Stefan Gillesen in Nature in 2012. It was found to really be on an extremely eccentric orbit that took it very close to SgrA star. Everybody was waiting for some accretion event. It has already passed there, but we still, it still may take time for the black hole to pick up with this accretion. And actually there's several of these stars, of these objects around, these compact dusty objects, whatever they are. Different people give them different name, the G objects or the dusty stellar objects, whatever is the preferred interpretation. One of them even has found to tidally interact with SgrA star at its passage. So Anna Churlo in a recent Nature paper claims that this is a completely new, unique class of objects that may have a common origin, be it mergers of binary stars or what they are. So I am very agnostic on this. Could be dust clouds, young stars, merged stars. I think each of these hypotheses has their own problems and their own attractiveness. So this is what the future research will bring us. And now I will wrap it up. So the future is going to be extremely exciting. So with the James Webb Space Telescope, we're going to be blown away, in particular because we have high angular resolution and sensitivity. So we will really be able to map all the structures nicely, overcoming the extinction of the Galactic Centre, break the color degeneracies that we have in near infrared due to the reddening, and then really classify stars photometrically, definitely using spectroscopy, measure Sagittarius star spectrum and variability. And then of course with the ELT, confirm or discard the hypothesis of YSOs near Sagittarius star. Also, what I have not mentioned, also lots of potential protoplanetary disks in the Galactic Centre and the young clusters. Thank you very much. I hope this has been a roughly complete overview. Please don't be mad at me if I left out your own favorite research. Thanks a lot.
Thank you so much. That was a really nice presentation going through these results. And in the Slack channel, I don't know if you can see, there's
Yes.
an enormous number of beautiful images of the Galactic Centre being posted. So given that we've got a bunch of people who have worked on this Galactic Centre in the past, I'm actually going to just invite some people to say a couple of words or comments to you. And I'm going to name some people. So the people that are posting a lot are Leo, Ryan, Enrique, Jim, Angel. So all these people, if you have any comments or things you want to say as a discussion area while we've got everybody online together, please go ahead.
It's a brief technical question, if I may, since you mentioned me first, I dare to ask first. Rainer, the Galactic Centre, of course, as you showed, is so full of emission. How do you observe it with VISIR? How do you do chopping and nodding, since do you chop far enough away that you're outside the emission? Or can you explain a little bit how this image that is unpublished was created?
Yes, this is a very, you need lots of time. You need lots of time and chop in all kinds of directions. From Spitzer, we know where we can chop. We need to go to the maximum, to 30 arc seconds. And early VISIR observations, they all suffer from chopping too small, chopping into other bright sources. And we cannot really know what kind of systematics we exactly introduce by chopping. So I think we have additional noise there simply because it's full of emissions. So it's a very good question, Leo. So what we have been doing is chop alternatively to east, west, north, south, but at 3 different angles. So to kind of minimize these effects. It's really difficult. And this is also going to be a difficulty with METIS, for example, in the ELT.
So I see that. Oh, go ahead.
So with the Galactic Cam observations that Roche published, so these we have also some issues because we have a slot of 2 arc-second by 25 arc-second. So that yes. Image is a combination of multiple mosaics with 1 arc-second offset each to each other. So it took me like 2 years to compile of that. But I didn't lose good.
Work, yes. I know, and I was so happy I didn't have to do this work. This was fantastic work.
Yeah, no, I mean the final image is just pretty good. So I'm glad that Galactic Cam did these observations. I think the only thing we need to increase the field of view now.
Yeah. Thank you for this absolutely fantastic image that you have just posted, Enrique, from Hawk, the magnetic fields. This is absolutely marvelous.
What? Yeah, the data speak by themselves.
Yeah, okay. Yeah, okay.
I see Pat Roach has turned his camera on, which is normally an indication of wanting to say something.
No, not especially. I think, that exactly what you said, the images really speak for themselves, and the complexity of the region, I think, is just astounding, and delving into it at higher sensitivity and resolution is bound to unearth all kinds of surprises.
Okay, there is a bit of a discussion going on between Ryan and Julian. I'm going to leave that. I might come back to that in a moment, but there is a question from Jim DeViser asking, won't James Webb saturate on the Galactic Centre?
No. Yes and no. You definitely have to use narrowband filters. We are working, and several groups are working on James Webb observations in imaging. I mean, spectroscopy is not such a big problem. It will be a tough sell to the committee because you will have lots of overheads, but I think it's just too unique, the Galactic Centre, to not observe it. You need to use narrowband filter and then you're okay-ish. The central parsec may be even a bit tougher. So the central parsec, yeah, you have lots of sources there saturated. Further out, you're doing okay with narrowband filters.
Wonderful, thank you. And I think the final question, Hans, I think you have your hand up. If you'd like to say or text your question, we'd love to hear it.
Can you hear me?
We can hear you just fine.
I'm calling from Chile, from Santiago. Okay, wonderful talk, Rainer. I hope to see you sometime when Spain is okay and we can watch some football again together. I was wondering, maybe I misheard. I mean, did anybody talk about the Hawk images by SOFIA, the Galactic Centre?
No, I omitted that, and I'm very sorry about that.
Of course, spatial resolution is not so good, but 10 arc seconds or so. But can you comment on it, or what did we learn in terms of the strength of magnetic fields close to the Galactic Centre?
I cannot do much comment on there. So if I would, yes, please.
I can comment. So we did the angular dispersion function analysis and the Davis-Chandrasekhar Fermi method in the whole spiral field, and then we obtained magnetic field strength of around 1 milligauss. And plasma beta is very low, which is actually telling you the magnetic field is dominating in the spiral arms and is constraining the gas flow against the galactic center, the center of the galaxy. It's very interesting. So the paper is still bright, and I think it's the first author is still writing the paper. So I don't know exactly if it's gonna be.
First author. Who will be writing the paper?
Darren Dowell, the PI of Hawk Plus.
Of course. Sorry. Yeah.
Yeah.
So that is still unpublished, correct?
Yes, it's still unpublished. It's been like a lot of pre-release, but the paper is not out yet because it's a lot of discussion regarding to the plasma beta parameter.
And could you conclude anything on the strength of the magnetic field also from the CANARICAM data?
I think we have to do the analysis. I think we can do it, perhaps.
Yeah, I mean, we did this, several years ago with the old 4 meter data, and again, you come up with fields of milligauss. You can't get an accurate direct measurement. You've got to do it by indirect arguments. But there have also been some Zeeman measurements which also indicate fields of the same order.